You've been told the solar system is orderly. Planets spin one way, orbit another, simple and predictable, but Venus quietly blows that picture apart. Here's a world almost the size of Earth, where a day is longer than its year, and the sun would rise in the west and set in the east. In this video, you're going to see how a near twin of Earth ended up spinning in reverse, why its day length is still changing by minutes right now, and how a mix of ancient impacts, brutal tides from the sun, and a runaway greenhouse atmosphere literally grabbed the whole planet and twisted its rotation into something. That should make you rethink what normal really means for worlds like ours. Start with scale. Venus is about 12,100 kilometers across, roughly 7,500 miles, around 95% of Earth's diameter. It orbits the Sun at about 0.72 astronomical units, around 108 million kilometers, about 67 million miles from the Sun. On paper, that looks like Earth's twin moved slightly inward. If you only had those numbers, you would expect a day length measured in hours, maybe a bit longer than Earth's, but still in the same ballpark. Instead, Venus does something completely different. Venus rotates once every roughly 243 Earth days relative to the distant stars, the sidereal day. Its year, its orbital period, is about 225 Earth days, so Venus goes around the Sun faster than it turns once on its axis. In simple terms, a true rotation day on Venus is longer than its year. Direction makes things stranger. Most planets, including Earth, rotate prograde. If you look down from above the Sun's north pole, they orbit counterclockwise and spin counterclockwise, so on the surface the Sun rises in the east and sets in the west. Venus is retrograde. In that same top-down view, Venus still orbits counterclockwise, but it spins clockwise. On the surface, if you could stand there and survive, the Sun would rise in the west and set in the east. So Venus is not just slow, it is reversed relative to its orbit. Here comes the next twist. You just heard that Venus takes 243 Earth days to complete one spin, but the day you would feel on the surface from one noon to the next is not 243 days. Because the planet spins backward while it moves forward along its orbit, the solar day on Venus, the time between two returns of the Sun to the same spot in the sky, is about 116.75 Earth days, a bit under 4 months. The crust takes 243 days to line up the same way with the stars, but the backward spin and the forward orbit combine so that the Sun laps the sky in roughly half that time. It is still an extremely long day, but it shows you that even a basic word like day has to be defined carefully here. The orientation of the spin axis adds another layer. A planet's axial tilt is the angle between its spin axis and a line straight up from its orbit. Earth has a tilt of about 23.4 degrees, which gives us our seasons. Venus has an axial tilt of about 177 degrees. Subtract that from 180 and you get about 3 degrees. So in practical terms, Venus's axis is only about 3 degrees away from straight up, but the whole axis is flipped over. The planet is rotating while almost completely upside down. The equator still lies close to the orbital plane, so Venus does not have strong seasons, but the direction of spin is inverted. This is a near-Earth twin that ended up in the rare upside down and backwards state. Now you might ask a basic question. How do we know any of this if Venus hides its surface under permanent cloud? In visible light, telescopes only see a bright, featureless cloud deck. You never watch surface markings move the way you can on Mars. The key tool is radar. Radio waves at the right wavelengths pass through the clouds, hit the solid surface and bounce back. Since the 1960s, large observatories on Earth have sent radar pulses to Venus and listened for the echoes. Shifts in the frequency of those echoes, caused by parts of the surface moving toward or away from us as the planet spins, tell you the rotation speed and the direction. Orbiters sharpen the numbers. NASA's Magellan spacecraft went into orbit around Venus in 1990 and used radar to map almost the entire surface. By imaging the same regions months apart and checking how far specific mountains and craters had moved in longitude, scientists measured how much the planet had rotated between passes and got a rotation period of about 243.02 Earth days. Years later, ESA's Venus Express mission from 2006 to 2014 looked again at some of the same features and found that to line the maps up you had to nudge that value slightly by a few thousandths of a day. Earth-based radar work from the late 1980s through the 2010s extended this tracking and gave an average sidereal day very close to 243.02 Earth days, with uncertainties below 1,000th of a day. The key point is that the values from Magellan, Venus Express and long-term radar differ by several minutes, more than the errors. The length of the day on Venus really drifts by a few minutes over spans of decades. So even now, Venus's rotation is not a perfectly fixed value. Something is still exchanging angular momentum with the planet and slightly changing how fast it spins. All of this is happening on a world with extreme surface conditions around 465 to 475 degrees Celsius, about 870 to 900 degrees Fahrenheit, and a pressure roughly 92 times Earth's sea level pressure. Yet through that, radar and orbiters have pinned down the spin period to better than 1,000th of a day, and have caught real changes of a few minutes over decades. So the picture you now have is a planet almost the same size as Earth, rotating so slowly that a true day is longer than its year, spinning in the opposite direction to most planets, almost completely inverted in axis, and with a day length that is not entirely stable. So here is the question that hangs over everything else. How does a near-Earth twin end up with a rotation that is slower than its year, reversed in direction, nearly upside down, and still drifting by minutes? Did Venus take one or more giant hits early on that flipped or slowed its spin? Has the Sun's gravity over billions of years been acting like a constant brake? Has the dense atmosphere, through tides and winds, actually grabbed the solid planet and forced it into this strange state? Or is the real answer a combination of all of these effects, adding up over the age of the solar system? To find out, you have to treat the rotation measurements themselves as your first big clue and dig into how, through clouds and across tens of millions of kilometers, we proved that Venus really spins backwards and that its bizarre day length is still changing. Here's the awkward question you have to face right now. Before you talk about any theories, how do you even know Venus is spinning backwards at all when you can't see its surface in normal light? Under a bright, featureless cloud layer, you cannot just watch a continent drift across the disk the way you can on Mars. So the first job is not to explain why Venus rotates differently. The first job is to prove, with hard measurements, that it really does. The basic trick is simple in idea and technical in execution. You stop using visible light and you switch to radar. Venus's clouds reflect most of the sunlight you see, but radio waves at the right wavelengths pass through those clouds, hit the solid ground, and bounce back. Since the 1960s, big radio observatories on Earth, including Arecibo in Puerto Rico, have sent radar pulses across the tens to hundreds of millions of kilometers between Earth and Venus, tens of millions of miles, and listened for the echo. Because Venus is rotating, part of the surface is moving slightly toward us, part is moving slightly away, and that motion leaves a tiny fingerprint in the return signal. This is where the Doppler shift comes in. When the surface moves toward you as it spins, the radar waves bounce back with a slightly higher frequency. When it moves away, the frequency is slightly lower. By looking at how the frequency changes across the disk of Venus, you can tell which limb is approaching and which is receding. If the eastern side is coming toward you and the western side is moving away, that tells you the planet is rotating one way. If it is reversed, the spin direction is reversed. Just from the pattern of these shifts, with no direct view of the ground, you can say Venus is rotating in a retrograde sense, opposite to Earth. Radar also gives you rotation speed. Distinctive radar bright features, linked to rough or high terrain, act like markers on the surface. By timing how long it takes for those bright patches to rotate back into the same viewing geometry, you can estimate the length of the sidereal day, the time Venus takes to turn once relative to the stars. Early radar campaigns already showed that Venus was slow, with a day hundreds of Earth days long, but the uncertainties were large. To pin the numbers down, scientists needed a platform that would orbit Venus, watch it for years, and map almost the entire surface at high resolution. That is where NASA's Magellan mission comes in. Magellan arrived at Venus in 1990 and spent from 1990 to 1994 in orbit, using synthetic aperture radar to build a detailed global map. It covered about 98% of the surface, imaging mountains, plains, and craters through the clouds at resolutions down to a few hundred meters, hundreds of yards. Because Magellan kept revisiting the same regions, scientists could pick out specific landmarks and track how far in longitude they moved between passes. By comparing these positions over a span of roughly 500 days, they could count how many degrees Venus had rotated in that time, and from that solve for the length of its sidereal day. The answer came out to about 243.0185 Earth days retrograde. That is the sidereal day, not the noon-to-noon solar day. This confirmed what Earth-based radar had hinted. Venus was not just slow, it was locked into a very long rotation period, with small error bars. You could stop there and say, fine, we know the day length, we can move on. But when Europe's Venus Express mission arrived in 2006 and started looking again, it exposed something more. Venus Express orbited the planet from 2006 to 2014, mainly studying the atmosphere, but it also used its instruments together with Magellan's maps to check surface positions years later. When researchers tried to line up the Venus Express data with Magellan's positions, they found that if they used the old 243.0185 day value, the features did not quite match. To make the two data sets agree, they had to adjust the rotation period slightly to about 243.023 Earth days with an uncertainty of plus or minus about 0.002 days. That sounds tiny, but on a planet where a single rotation lasts about 21 million seconds, this tweak corresponds to a shift of a few hundred seconds, several minutes over roughly 16 years. That is too large to write off as measurement noise. Now the picture changes. You're not looking at a perfectly fixed rotation, you're looking at a day length that actually drifts. To test this, you go back to the radar technique from Earth, but now you do it over a much longer baseline. Between 1988 and 2017, teams used powerful ground-based radar to bounce signals off Venus many times and track its rotation. By combining almost 3 decades of observations, they derived an average sidereal day length of about 243.0212 Earth days, with an uncertainty of only around 0.0006 days, roughly a minute over the full 243 days. Magellan's value, Venus Express's adjusted value, and the long-term Earth radar value all cluster around the same number, just over 243 days, but they do not match perfectly. The differences are small in absolute time, a few minutes, but the uncertainties are even smaller. That means the changes are real. The length of the Venusian day is not constant from one decade to the next. And through the radar Doppler signatures, all of these data sets agree that the spin is retrograde. The surface rotates opposite to the orbital direction. So why does this matter for the deeper question of why Venus rotates differently? Because if the planet's strange rotation were just the frozen remnant of a single accident in the distant past, you would expect the day length today to be rock solid. Instead, what you see is a rotation that is both unusual and still being modified. Something is actively applying torque to Venus right now, over human timescales, trading angular momentum between the solid planet, its atmosphere, the sun's gravity, and maybe its core. The drifting day length is your first clear sign that Venus's backward spin is not just a historical curiosity, it is a live, evolving state that any serious explanation has to match. Which raises the tension for the next step. If the measurements are this precise, and the changes are this real, what kind of forces are strong enough and persistent enough to slow an Earth-sized planet to a 243-day retrograde spin and then keep nudging that spin by minutes over just a few decades? You keep hearing that Venus is weird, but that only means something if you know what normal looks like. So before you blame Venus for breaking the rules, You have to ask, what is the default behaviour for planets? How do most of them spin? And how far away from that standard did Venus actually go? Take the simple version first. In our solar system, the default spin is prograde, same direction as the orbit. If you look from high above the Sun's north pole, most planets go around the Sun counterclockwise, and they also rotate counterclockwise. On the ground, that shows up as a familiar pattern. The Sun rises in the east, crosses the sky, and sets in the west. Earth does one full spin in about 24 hours, Mars takes about 24.6 hours. Jupiter, even though it is huge, spins in under 10 hours. These are fast forward spins that match the orbital direction. Their axes are tilted, but not flipped. Earth's spin axis is tilted about 23.4 degrees away from straight up relative to its orbit. That tilt gives us seasons. Mars is tilted about 25 degrees, which is why it also has seasons that roughly make sense to us. Jupiter barely leans at all, only around 3 degrees, so it has very mild seasons, almost none. All of these tilts mean the planets are leaning, but they are not upside down. They are not rotating backwards. The spin direction and the orbit direction line up in the same basic sense. Now drop Venus and Uranus into that picture, and you see immediately that they do not follow this pattern. Both of them have what scientists call extreme obliquities, extreme tilts. Uranus has a tilt of about 98 degrees, Venus has a tilt of about 177 degrees. In practical language, Uranus is tipped so far over that it is almost rolling on its side, while Venus is rotated so that its axis is almost completely flipped. But the important detail is, they got to these extreme states in different ways, and that matters for their spin histories. For Uranus, a tilt around 98 degrees means its spin axis lies almost in its orbital plane, like a ball knocked onto its side. It still rotates in the same sense as its orbit, but that rotation is happening around a sideways axis. For Venus, a tilt around 177 degrees means something different. Subtract 177 from 180, you get about 3 degrees. That means Venus's axis is only about 3 degrees off straight up, but the whole axis is reversed. The planet is effectively upside down. So in terms of how much it leans relative to the orbital plane, Venus is actually almost upright, only a small tilt, but with the direction of spin inverted. That is a subtle but crucial difference, and it is why Venus and Uranus are both odd, yet not in the same way. Here is a point that often confuses people. Why do scientists say Venus has a tilt of 177 degrees instead of just saying 3 degrees and calling it a day? The answer is a definition trick, and it is all about how we define the north pole of a planet. By convention, astronomers use a right-hand rule tied to the direction of rotation. You curl the fingers of your right hand in the direction the planet spins, your thumb points to the North Pole. For planets that rotate prograde, like Earth, that North Pole ends up on the same side of the orbital plane as the Sun's North Pole. For a retrograde planet like Venus, if you keep that rule, the pole that counts as north ends up on the opposite side of the orbital plane from what your intuition might say. So when you measure the angle between Venus's spin axis and the line straight up from its orbit, sticking to that convention, you get about 177 degrees, not 3. Writing 177 degrees encodes two things at once: a small effective tilt, about 3 degrees, and an inverted axis, which carries the information that the spin is retrograde. That is why scientists keep this slightly awkward number. It bakes the upside down and backward status directly into the tilt value. Now, connect this to the orbit itself. Venus still orbits the Sun in the same direction as Earth, counterclockwise when you look from above the Sun's North Pole. It goes around once every 225 Earth days or so, at a distance of about 0.72 astronomical units, around 108 million kilometers, about 67 million miles. On that large scale, it behaves like a normal inner planet. The problem is the spin, not the path. Because Venus rotates retrograde, the equator is effectively moving opposite to the orbital direction. If you mark a point on the equator and track it from above, the planet's bulk is turning clockwise while it orbits counterclockwise. That mismatch between spin direction and orbital direction is the core of every serious model for Venus's past, Because in the early solar system, when planets form from a spinning disk of gas and dust, the natural outcome is prograde rotation. Something had to push Venus away from that. And this is where different stops being a casual label and becomes a serious physical clue. Out of all 8 major planets, only 2, Venus and Uranus, ended up with such extreme spin states, one nearly upside down and retrograde, the other almost on its own. That tells you these states are not common. They are rare endpoints that require either violent events, like giant impacts, or very long-term, finely balanced torques from tides and atmospheres acting over billions of years. So when you look at Venus's rotation now, you are not just seeing a quirky detail, you are looking at a fossil record of everything that has pushed and twisted this planet since it formed. A giant collision early on could have flipped or slowed its spin. Solar tides, over the immense timescales, could have drained angular momentum and tipped the axis. A dense atmosphere could have grabbed the crust through tides and winds and dragged the rotation into a new configuration. Whatever the exact mix, the fact that Venus is one of the only planets that reached this extreme state means its spin history has to be long, complex, and full of strong interactions, which sets up the next hard question you have to answer. If Venus did not just randomly decide to spin backwards, what are the actual mechanisms that can grab a whole planet, strip away most of its original rotation, and then force it into a slow, retrograde, almost upside-down state? And could those same forces, if left running for billions of years, still be reshaping its day length right now? How do you slow an entire planet without ever touching it? No engines, no collisions, just pure gravity from far away. That is what the Sun has been doing to Venus for billions of years, and if you want to understand why Venus rotates the way it does, you have to start with tides. Not the ocean kind, but tides in rock and air. Here is the basic idea. Any spinning planet is not a perfect sphere. Rotation makes it bulge a bit around the equator. That bulge is extra mass, and the Sun's gravity pulls on it. If the planet is rotating faster than it orbits, the equatorial bulge is dragged a little ahead of the direct line connecting the planet and the Sun. Gravity does not like that offset. The Sun pulls back on the bulge trying to line it up, and that pull creates a torque, a twisting force that acts like a brake on the rotation. No contact, no impact, just gravity slowly stealing spin energy and turning it into heat inside the planet. The key thing is time scale. This is not something you notice over a human lifetime. Tidal braking works over hundreds of millions to billions of years. But given enough time, even a small torque can take a planet that once spun in maybe 10 hours, like a young Earth, and slow it down until the day length is measured in months. You can see 2 different tidal outcomes right next to each other in the inner solar system, Mercury and Venus. Mercury orbits closer to the Sun than Venus does, at about 0.39 astronomical units, around 58 million kilometers, roughly 36 million miles. The solar tides there are stronger, yet Mercury did not become a slow retrograde spinner. Instead, it got locked into a 3-to-2 spin-orbit resonance. It rotates 3 times on its axis for every 2 trips around the Sun. Its sidereal day is about 58.6 Earth days, and its solar day noon to noon is about 176 Earth days. Venus is farther out at 0.72 AU, but it is almost at a tidally locked state, with a rotation period of about 243 Earth days, and that rotation is retrograde. So closer in, Mercury ends in a neat resonance. Farther out, Venus ends in a slow backward spin. That tells you tides are not acting on identical systems. Mercury has almost no atmosphere. Its surface pressure is effectively 0 compared with Earth. Venus has a roughly 90 bar atmosphere, about 92 times Earth's sea level pressure. On Mercury, solid body tides in the rock dominate. On Venus, you have solid tides and you also have huge atmospheric tides, waves of dense gas being heated by the Sun and shifting mass around. That extra piece changes the entire outcome. Now talk about the long view. If you start with a Venus-like planet with a normal prograde spin and you only include solid body tides from the Sun, models show a simple trend. Over billions of years, the spin slows down, the day length increases, and the rotation tends toward a state where the same side of the planet keeps facing the Sun, or some simple resonance close to that, and it stays prograde. So with just rock and gravity, you would expect a slow, forward-rotating Venus, maybe something like Mercury's resonance, not a flipped retrograde one. Once you add a dense atmosphere and you let the Sun heat that air unevenly, the story changes. Atmospheric tides come from the daily heating and cooling of the atmosphere as the planet rotates under the Sun. Warm regions expand, cool regions contract, and the whole air mass develops pressure waves that move around the planet. Those waves create their own bulges, areas of higher pressure and density that are not exactly aligned with the Sun. The Sun's gravity pulls on those atmospheric bulges too, just like it pulls on the solid equatorial bulge, and that creates another torque. The important part is direction. The atmospheric tide can push the rotation in a different direction from the solid tide. Depending on rotation rate, orbital period, and how the atmosphere responds to heating, the net torque from the atmosphere can actually favour retrograde rotation. So instead of only breaking a prograde spin toward a simple locked state, the combined solid and atmospheric tides can drive the planet toward a slow, stable retrograde state. Right now, Venus seems to sit close to a balance point between these competing torques. On one side, the Sun's gravitational pull on the solid body still tries to drag the rotation toward a simple tidally locked configuration, where the same hemisphere would always face the Sun. On the other side, the thermal tides in the thick atmosphere tend to push the spin towards slow retrograde. The measured rotation period of about 243 days looks like an equilibrium between these two, a compromise the system settled into over billions of years. That balance is not perfect. The changes of a few minutes in day length over decades that you saw from Magellan, Venus Express, and ground-based under radar are the signature of a planet hovering near a delicate torque balance, not a planet that has completely frozen into one state. The solid tides, the atmospheric tides, and probably interactions with the interior are all still trading angular momentum. The result is small but real fluctuations around that 243-day average. To make this more concrete, look at the speeds involved. Venus's equator is about 38,000 kilometers around, roughly 24,000 miles. If it takes 243 Earth days to make one full rotation relative to the stars, that works out to an equatorial speed of about 7.3 kilometers per hour, around 4.5 miles per hour. That is slower than a normal human jogging pace. Earth's equator, by comparison, is moving at about 1,670 kilometers per hour, roughly 1,040 miles per hour. Somehow, over its history, Venus went from a likely fast prograde spin similar in scale to Earth's, down to a crawl where the ground at the equator drifts along at walking speed. There is no way to get from hundreds of meters per second to 2 meters per second at the equator without a long, sustained braking process. Tidal torques, working continuously over billions of years, are the only realistic mechanism that can remove that much rotational energy from an Earth-sized planet and then hold it near a slow spin state. The Sun's gravity has had that long, and Venus's dense atmosphere has given it a powerful handle. But here is the part you cannot ignore. If atmospheric tides are strong enough to fight against the Sun's direct pull on the solid planet, and even flip the rotation into retrograde, then the atmosphere itself is not just a passenger, it is an active driver. So the next question you have to face is simple and uncomfortable. What exactly is that atmosphere doing to Venus's spin right now, and how can a layer of gas, no matter how thick, grab hold of an entire rocky planet and make it rotate backwards? Here's the part that sounds almost ridiculous at first. How can a layer of gas, even a thick one, actually grab a whole planet and change how it spins? Rock feels solid, atmosphere feels soft. But on Venus, the air is so dense and so fast that it behaves more like a global engine than a thin shell. You've already seen the sun pulling on the planet through tides. Now you have to let the atmosphere join the fight. Start with what the air is actually doing. Up at the cloud tops, about 60 to 70 kilometers above the surface, Venus's winds race around the planet in roughly 4 Earth days. That's about 360 kilometers per hour, around 225 miles per hour. Meanwhile, the solid planet takes 243 Earth days to rotate once. So in terms of rotation rate, the atmosphere is lapping the surface by a factor of about 60. That state has a name, superrotation. It just means the atmosphere is rotating much faster than the solid body underneath. If you stand on the surface, in theory, the ground under your feet is crawling west to east at about 7.3 kilometers per hour, roughly 4.5 miles per hour, because the sidereal day is so long. Above you, the clouds are blasting around the planet in the opposite direction in 4 days. The air is not just drifting, it is carrying an enormous amount of angular momentum compared with the crust. It is like having a gigantic high-speed belt wrapped around a very slow wheel. When that belt changes speed or pattern, it can transfer some of its spin to the wheel, or take some away. Now bring in sunlight. As Venus rotates under the sun, the day-side atmosphere heats up, the night side cools down. Warm air expands and becomes less dense. Cool air contracts and becomes more dense. This cycle creates pressure waves in the atmosphere, patterns of slightly higher and lower pressure that travel around the globe. These are atmospheric tides. You get a weaker version on Earth too, but our atmosphere is thin compared to Venus, and our surface pressure is only about 1 bar, 1 Earth atmosphere. On Venus, you are dealing with roughly 90 bar, about 92 times Earth's sea level pressure, in a carbon dioxide heavy atmosphere. The mass of that air is huge, so when it shifts around, the effect on the planet's spin is not small. Those atmospheric tides create a kind of air bulge, regions where the atmosphere is slightly denser and under higher pressure. Because heating and cooling are not perfectly in sync with the position of the sun in the sky, the bulge does not sit exactly on the line connecting Venus and the sun. It gets dragged a little ahead or behind. The sun's gravity pulls on this shifted bulge, just like it pulls on the solid equatorial bulge of the planet. That pull is a torque, a twist, and depending on how the bulge is offset, that torque can act to accelerate or decelerate the planet's rotation, and it can favour a retrograde spin, so you now have 2 tidal systems operating at once. The solid planet feels a gravitational tide from the sun that tends to slow and align the spin in one way. The atmosphere feels thermal tides from sunlight that move mass around and create a secondary bulge, which the sun then pulls on in a different phase, adding a torque that can push the rotation towards slow retrograde. In a dense atmosphere like Venus's, this second effect is strong enough that you cannot treat the air as a passenger anymore. It is one of the main drivers. There is another, more local way the atmosphere and surface connect, through what are called mountain waves. Those super fast winds at the cloud tops are not moving over a perfectly flat world. Venus has highland regions, broad mountain ranges and plateaus that reach several kilometers above the average surface, several miles. When fast winds flow over these obstacles, they generate waves in the atmosphere, like ripples in a fluid, but stretched vertically and horizontally on a planetary scale. Data from Venus Express showed signs of these waves as large, stationary patterns in the clouds locked to underlying topography. They are called stationary gravity waves, not because of gravity in the sense of weight, but because buoyancy and gravity together shape them. These waves create long-lived regions of higher and lower pressure in the atmosphere, fixed over certain mountains or plateaus. Those pressure patterns are another way for the air to push on the solid surface, adding small torques that either speed up or slow down the spin. Over short times, each effect is tiny, but over years to decades, constant exchange of angular momentum between the super-rotating atmosphere and the crust can add up to real changes in the rotation period, measured as differences of a few minutes in day length. That is exactly what the radar and spacecraft data show. The day on Venus is not locked at one sharp value. it moves slightly as the atmosphere shifts. If you try to keep track of all these pushes and pulls, it starts to look like an accounting problem, a torque ledger. On one side, you have the sun's gravitational tides on the solid planet, trying to drag the rotation toward a tidally locked prograde state. On the other, you have thermal atmospheric tides, driven by sunlight heating that massive CO2 atmosphere, trying to push the spin toward a slow retrograde state. On top of that, you have mountain waves and internal processes adding smaller corrections. Researchers like Alexandre Correa and colleagues have modelled this system and found that for a planet with Venus's mass, distance from the Sun, and atmospheric thickness, you do not get an infinite range of possible final spins. You get a small set of stable end states, attractors. Some are slow prograde rotations, some are slow retrograde rotations. Venus's current 243-day retrograde spin sits right in one of those stable basins. The idea is that no matter what reasonable spin Venus started with, fast and prograde, slow or even slightly retrograde, the combined action of gravitational and atmospheric tides over billions of years would nudge it toward one of these few allowed states. So the atmosphere is not just responding to the spin, it is helping select the spin. By pumping angular momentum into or out of the solid planet, it steers Venus into that slow backward rotation and then helps hold it there, with small fluctuations. Every change in global wind patterns, every long-lived wave over a mountain range is part of that ongoing negotiation between air and rock. The key point for you is this: Venus does not just happen to have a weird rotation left over from some ancient event, and it does not just happen to have a thick atmosphere. The two are linked. The atmosphere is actively maintaining that slow retrograde spin. Those thick clouds racing around in 4 days are part of a huge invisible flywheel, storing and releasing angular momentum and keeping the surface crawling backwards at walking speed. And that pushes you toward an even sharper question. If the atmosphere can control the spin like this, was it always the main player, or did something more violent have to happen? Something that knocked Venus off its original rotation and gave the tides and the atmosphere a completely different starting point to work from. What if Venus didn't just slowly drift into its weird rotation? What if it got hit so hard that its original spin was basically erased? Tides are good at shaving away rotation over billions of years, but they are slow. A single giant impact, early in the solar system's history, can change a planet's spin in minutes. So if you already accept that a collision helped make Earth's moon, that another one probably stripped Mercury's mantle, and that Uranus was likely knocked onto its side, it is completely reasonable to ask, did Venus also take a huge hit that started this whole backwards, upside-down story? We know from models of the early inner solar system that it was crowded with large bodies, some as big as Mars, tens of millions of kilometers apart, crossing orbits, colliding, merging. In that environment, you do not get smooth, gentle evolution. You get rare, extremely energetic events that dominate the final outcome. When a Mars-sized object hits a planet, it does not just make a big crater, it dumps a huge amount of angular momentum into the target. Depending on the angle and speed, that angular momentum can speed up the spin, slow it down, tilt the axis, or flat out reverse the rotation direction. So putting giant impacts on the table for Venus is not a stretch. It is almost required, given how extreme its spin is. Modern computer simulations take this seriously. Researchers run large sets of impact scenarios, varying impactor mass, speed, and angle, and then watch what happens to a Venus-like planet. One key test is, can you end up with a slow retrograde rotation like we see today? Another test is, can you do that without leaving a big moon behind? For Earth, the most accepted scenario is a giant impact that both changed our spin and threw enough debris into orbit to form the moon. Venus, by contrast, has no moon at all, not even a small one. Some simulations have found a way to hit both targets at once. If an impactor strikes Venus at the right angle and speed, and most of the debris it throws off ends up orbiting inside the distance where an orbit would match Venus's rotation, what's called the synchronous orbit. then that material does not stay out as a separate body. It spirals back in, reaccreting onto the planet instead of clumping into a stable satellite. In that case, you can flip or strongly alter Venus's spin, but the leftover debris does not survive as a moon. You are left with exactly what we see today, a planet with an odd rotation and no natural satellite. So how big a hit are we talking about? Roughly, you are looking at an impactor with a mass from a few percent up to maybe a few tens of percent of Venus's mass. Venus itself is about 4.9 times 10 to the 24th kilograms, about 81.5% of Earth's mass, so even a few percent of that is enormous. Speeds in these scenarios are on the order of 10 to 30 kilometers per second, which is about 22,000 to 67,000 miles per hour. At those speeds, each kilogram of impactor carries enough kinetic energy to melt or vaporize many times its own mass in rock. The angular momentum involved is easily enough to turn a roughly 12,000 kilometer wide planet, about 7,500 miles, from a fast prograde spin to a slow or even reversed spin. The exact details matter. A head-on hit tends to mainly change the spin rate, slowing or speeding the rotation. A glancing off-center impact is more effective at tilting the axis and flipping the direction. The time of the impact matters too. If Venus is still partly molten, its interior can redistribute mass more easily, and the final tilt can be different from what you'd get if the planet were already solid. But the main takeaway is simple. You do not need hundreds of small nudges to get Venus into a bizarre spin state. One or a few really huge impacts at the right angles could do most of the job in one step. Now you have two broad origin stories on the table. One says Venus started with a normal prograde spin like Earth, then the Sun's gravitational tides and the planet's own atmosphere slowly twisted that rotation over billions of years into the slow retrograde state you see today. The other says a giant impact or series of impacts violently changed its spin early on, maybe even flipped it, and then tides and atmosphere only had to smooth and fine-tune the result. Impacts are attractive because they give you a fast, dramatic explanation. Tidal and atmospheric models are attractive because they show that, even without a big hit, a Venus-like planet can still evolve into a slow, backward spinner under long-term forces. The current thinking in the field does not insist on one single answer. Instead, it leans toward a combination. A giant impact may have set the initial conditions by slowing or flipping the spin and heating and mixing the interior. After that, solar tides and atmospheric tides had billions of years to act, gradually steering Venus into one of the stable end states that the torque balance allows, such as the slow retrograde rotation we measure now. In this view, the impact provides the big shove and the tides provide the long, steady steering. But this is still a hypothesis. So what would it take to really prove or disprove the giant impact idea for Venus? You would want much better data on the planet's interior and crust. A huge collision can leave behind signatures, a core that is offset or proportionally different, large-scale mixing in the mantle, global resurfacing events that erase older crust and lay down a more uniform layer, unusual patterns in gravity and topography that hint at an early global reset. You might also look for evidence that a former debris disk existed and then fell back in, for example, subtle chemical differences in the outer layers. To get that level of detail, you need hardware on site. That means orbiters with higher resolution radar mapping to track fine details in topography and gravity, and landers that can last long enough in 465 degrees Celsius heat and 90 bar pressure to deploy seismometers. Seismology is especially important because it lets you probe core size, core state and mantle structure. You could then compare Venus's internal structure with Earth's and see whether a giant impact is required to explain it, or whether more gentle evolution could do the job. So right now, the honest answer is that a massive impact remains a strong candidate for why Venus's spin looks so strange, but it's not the only path the physics allows. And that uncertainty points you back to a crucial observation. If a giant collision set Venus spinning oddly billions of years ago, its rotation should now be mostly a fossil, stable and fixed. Yet you already saw that the length of the day is still changing by minutes over just a few decades. something today is still adjusting the spin. Which forces you into the next question. If the big violent events are long over, what are the active processes right now that make a Venusian day creep shorter or longer by minutes? And what does that say about how alive or dead this planet really is, dynamically? If Venus was just the leftover wreckage from some ancient hit and run, its rotation should be boring now, fixed, predictable, but it is not. When you actually compare measurements across decades, you see something unnerving. The length of a Venusian day is drifting by minutes over human timescales. For a planet, that is fast. Start with the data. Magellan measured Venus's rotation in the early 1990s and got a sidereal day of about 243.0185 Earth days. Years later, Venus Express and ground-based radar campaigns remeasured it and found values closer to 243.02, 1 to 243.023 days. The difference between those numbers is only about 0.004 to 0.005 days, but that is roughly 6 to 7 minutes. Spread over 16 to almost 30 years between measurements, that is a real, repeatable shift, not just a random error bar. So from one observing epoch to another, the length of a Venusian day changes by several minutes. At first glance, 7 minutes on a 243-day rotation sounds trivial, but look at the fraction. A Venus day is about 243 Earth days. Multiply that by 24 hours per day, you get around 5,800 hours. 7 minutes is a small slice of that, but it still corresponds to a fractional change on the order of 1 part in 100,000. For an entire planet, that is a big adjustment, because it applies to every bit of mass from the core to the crust. Translate that into speed at the equator. Venus has a radius of about 6,052 kilometers, roughly 3,760 miles. The circumference at the equator is about 38,000 kilometers, around 24,000 miles. If the planet spins once in 243 days, the equatorial speed is about 7.3 kilometers per hour, roughly 4.5 miles per hour, slower than a relaxed jog. Change the rotation period by that tiny fraction, and you change the equatorial speed by a few tens of centimeters per second, something like half a meter per second, roughly 1 or 2 feet per second. That does not sound impressive until you remember that this change applies to the entire equator at once, thousands of kilometers long, and all the mass tied to it. You're talking about a walking pace difference, but scaled up to a whole world. So what is moving that much angular momentum around? The numbers point straight back to the atmosphere. You already saw that Venus's clouds at the top of the atmosphere circle the planet in about 4 days at around 360 kilometers per hour, about 225 miles per hour, while the surface crawls along in 243 days. That atmosphere at around 90 bar, 92 times Earth's surface pressure, holds a huge amount of mass and therefore a huge amount of rotational energy and angular momentum. In models, when global wind patterns in that super-rotating atmosphere speed up or slow down, the total angular momentum of the Venus system has to stay roughly conserved. If the atmosphere takes on a bit more angular momentum by spinning faster, the solid planet has to give some up, and its rotation slows slightly. If the winds lose angular momentum, the solid planet can gain it back and spin a bit faster. The exchange is not magic. It happens through friction and pressure forces at the interface between air and rock, and through mountain waves locked to highland regions that act like coupling points. Those stationary waves that Venus Express saw over big plateaus and the mountains are probably part of the mechanism. They create long-lived high and low pressure regions in the atmosphere tied to the surface topography. As the super-rotating winds slam into those regions, they push on the ground. Over years, that push adds up. You get a slow transfer of angular momentum that shows up at the planetary scale as a small change in rotation rate and day length on the order of minutes. Gravitational tides from the sun are still there in the background, constantly trying to break the spin and push Venus toward a simple resonant or locked state. And inside the planet, the core and mantle may not rotate perfectly together. so electromagnetic and viscous coupling at the core mantle boundary can add another small source of spin variations. Just like tiny changes in Earth's core and mantle motion can shift our day length by milliseconds. But for Venus, on decade timescales, the dominant player appears to be the atmosphere, because it is both massive and fast. So the picture you end up with is not a weird rotation that froze a long time ago. It is a rotation that is still being adjusted in real time by a deep, fast, heavy atmosphere that behaves like a huge angular momentum reservoir. The winds act like a storage tank, temporarily holding extra spin or giving it back, and the solid planet responds by changing its day length just enough to keep the total budget balanced. This directly breaks the common mental image of Venus as a dead world where nothing big changes anymore. Yes, the surface is baked rock at around 465 degrees Celsius, roughly 870 degrees Fahrenheit, under 90 bar pressure. There is no water cycle, no plate tectonics that we can clearly see, no obvious seasonal snow or ice. On the ground, it looks frozen in a hellish state. But dynamically, in terms of rotation, Venus is more like a slowly turning top that is being nudged constantly by a powerful global atmosphere wrapped around it. The changing day length is your hard, measurable proof of that. It is the observational fingerprint of an ongoing fight between rock, air, and sunlight. Solar heating drives superrotation and atmospheric tides. Those tides drive angular momentum into or out of the solid planet. The sun's gravity pulls back through solid body tides, and the core mantle system adds smaller effects. The result is a day that is not fixed, but shifts by minutes on human timescales. And that leads to a bigger, more uncomfortable question. If Venus's spin can still be moved around this much by its environment, why did this particular planet, and not Earth or Mars or Mercury, end up in such an extreme sensitive state? With a slow retrograde rotation that its atmosphere can actually control. What is so special about Venus that turned its rotation into the most finely tuned, easily disturbed spin in the inner solar system? So now you have the big question staring you in the face if tides, atmospheres, and maybe giant impacts can twist a planet's spin this much. Why isn't every planet in the solar system as messed up as Venus? Why is Venus the one with the backward, ultra-slow rotation, while Earth, Mars, and the rest look almost reasonable by comparison? Start with the obvious comparison, Earth. Earth has a real atmosphere, weather, storms, jet streams, but the surface pressure is about 1 bar, not 90 bar. Our air just does not have the same mass as Venus's. More important, Earth has a big moon, about a quarter of Earth's diameter, orbiting at roughly 384,000 kilometers, about 239,000 miles away. That moon raises strong tides in Earth's oceans and, to a lesser extent, in the solid planet. Those lunar tides have been draining Earth's rotation for billions of years, taking us from early days that were maybe 5 to 6 hours long to the 24-hour day you live with now. On Earth, the moon dominates the tidal torque budget. The atmosphere plays a role, but it never gets to own the spin the way it does on Venus, because the lunar tide is bigger and the atmosphere is lighter. So Earth ended up with a moderately long prograde day, and the axis tilt of about 23.4 degrees stayed in a comfortable range, stabilized by the moon. The system never drifted into the very slow sensitive spin regime where atmospheric tides can push the planet around. Now look inward at Mercury. Mercury gets blasted by solar tides that are much stronger than what Venus feels, because it orbits at about 0.39 astronomical units, around 58 million kilometers, roughly 36 million miles from the Sun. But Mercury has essentially no atmosphere. Its surface pressure is so close to zero that atmospheric tides are negligible. That means there is no massive, moving air layer to store angular momentum or fight back against the Sun's direct pull on the solid planet. In that situation, the outcome is very different. Solar gravitational tides alone slow and shape Mercury's rotation until it falls into a 3 to 2 spin-orbit resonance, 3 rotations for every 2 orbits. The sidereal day is about 58.6 Earth days, and the solar day, noon to noon, is about 176 Earth days. Same sun, same tidal physics, but with no atmosphere, the planet ends up in a clean resonance instead of a slow retrograde spin. That contrast tells you how crucial the presence or absence of a deep atmosphere really is. Move outward again to Mars. Mars has an atmosphere thick enough for dust storms and weather, but its surface pressure is only about 6 millibars on average, less than 1% of Earth's. That is nowhere near Venus's 90 bar, so Mars does not have the mass in its atmosphere to generate huge atmospheric tides with serious torque on the planet. Its day is about 24.6 hours, very close to Earth's, and its rotation has stayed in that ballpark. Solar tides at Mars's distance are weaker than at Venus, and the thin atmosphere cannot compensate. Result: Mars keeps a simple, fast prograde spin, and then the gas giants, Jupiter, Saturn, Uranus, Neptune. These planets have enormous atmospheres, far thicker than Venus's, but they also have enormous angular momentum. Jupiter spins in about 10 hours, Saturn in about 10.7 hours, Uranus in about 17 hours, Neptune in about 16 hours, and their radii are tens of thousands of kilometers, tens of thousands of miles. The linear speeds at their equators are many kilometers per second. They also sit far from the Sun, so solar tides are weak out there. The Sun just does not have enough leverage at those distances to significantly slow or flip their spins over the age of the solar system. Their atmospheres are massive, but the initial rotation is so fast and the solar torque is so small that the basic spin state hardly changes. Among the gas giants, Uranus is the one that looks as strange as Venus in terms of tilt. Uranus's axis is tilted by about 98 degrees, so it is basically on its side, rotating around an axis that lies almost in its orbital plane. The most likely cause is one or more colossal impacts early in its history, similar to the kind of event we talked about for Venus, but happening in the outer solar system. The difference is the distance from the Sun. Out where Uranus orbits, at about 19 astronomical units, roughly 2.9 billion kilometers, about 1.8 billion miles from the Sun, solar tides and solar-driven atmospheric tides are extremely weak. Once Uranus got knocked onto its side, very little has happened to its spin since. The impact set the state, and tides have not had the strength to drag it somewhere else. Venus looks like a mix of both worlds. It has an extreme spin state like Uranus, but it lives in the inner solar system where solar gravity and solar heating are strong. It may have taken a big impact, but it did not stay as a pure impact fossil. Tides and atmosphere kept working on it. That combination, an inner planet with both a potential impact history and strong tidal evolution, is what makes Venus special. Put all this together, and you see why Venus stands out. It is roughly Earth-sized, with a radius of about 6,052 kilometers and a mass about 81.5% of Earth's, so it was a big, attractive target for early giant impacts. It orbits at 0.72 astronomical units, closer to the Sun than Earth, so solar gravitational tides and solar heating are stronger, giving the Sun more power to break its spin and drive atmospheric tides. And it ended up wrapped in a roughly 90 bar, CO2-dominated atmosphere that supports super rotation, atmospheric tides, and strong coupling to the surface. Earth shares the size, but not the atmosphere or the lack of a big moon. Mercury shares the strong solar tides, but has almost no atmosphere. Mars shares the rocky nature, but is smaller, farther out, and has a thin atmosphere. Uranus shares the extreme tilt and likely impact-driven history, but it is far from the Sun where tides are weak. Venus is the one object that sits at the intersection of all the main spin-altering processes: Earth-like size, inner orbit tides, thick atmosphere, likely early collisions. So when you ask, why this planet, not that one, the answer is that Venus sits in a narrow zone where impacts, gravitational tides, and atmospheric tides are all strong enough to matter, and they have had billions of years to interact. It became the solar system's best laboratory for how a planet's rotation can be completely rewritten, not just slowed a little or tilted a bit, but driven into a slow, retrograde, tightly balanced state that is still evolving. And that sets up the next step you have to take. If Venus is really the outcome of all these forces working together, then you cannot keep treating it as a simple solid ball with an atmosphere on top. You need to go deeper and ask how the internal layers, the core and the mantle, are participating in this slow, continuous reshaping of the planet's spin. What if the real reason Venus spins the way it does isn't just outside in tides and atmosphere, but buried deep inside the planet itself? So far you've been treating Venus like a solid ball with air glued on, but that's not how real planets work. They have layers, those layers move differently, and those differences can feed straight back into the rotation. Based on its mass and size, Venus looks structurally a lot like Earth. It's about 81.5% of Earth's mass, and its radius is roughly 6,052 kilometers, about 3,760 miles. From that, plus what we know about rock and metal at high pressure, the standard picture is simple: an iron-rich core in the center, a thick silicate mantle around that gear, and a comparatively thin rocky crust on top. So if you could slice Venus in half, you'd see something broadly Earth-like in composition. Not a gas ball, not some exotic strange material, just hot metal and rock layered under insane pressure and temperature. But even with that simple three-layer picture, rotation gets more complicated. The big question is, what state is the core in? If the core is at least partly liquid, like Earth's outer core, it doesn't have to spin at exactly the same rate as the mantle and crust. The liquid metal can rotate a bit faster or a bit slower than the solid rock above it. Where those two meet, at the core-mantle boundary, friction and electromagnetic forces act like internal brakes and clutches, constantly trying to bring the spins into line. On Earth, we actually see the effect of this internal coupling. Tiny changes in core flow can tweak the day length by milliseconds, and we have to account for that when we keep precise time. For Venus, we don't have that level of detail yet, but the physics is the same. If the core is liquid or partly liquid, and the mantle convection is doing its own thing, then viscous and electromagnetic torques at that boundary will be quietly trading angular momentum between the deep interior and the outer shell. On their own, those torques probably only make small changes, but when you combine them with the much larger atmospheric and tidal effects, they can contribute to the multi-minute day-length variations we measure over decades. Now, think about how heat flows through the planet. The core is hot, heated by leftover formation energy and radioactive decay. That heat leaks outward into the mantle and eventually escapes through the surface. As it does, it drives mantle convection, slow creeping motion of hot rock rising and cooler rock sinking. The way that convection happens matters for rotation, because it changes how mass is distributed inside the planet. If Venus had active plate tectonics like Earth, slabs of crust would sink, new crust would form, and mass would constantly be rearranged in moving plates. If instead Venus is in a stagnant lid regime, where the crust is one mostly unbroken shell and convection happens mostly below it, the pattern is different. Either way, whenever you shift large amounts of mass inside a rotating planet, you slightly change its moments of inertia, basically how hard it is to spin around different axes. Change that and you can slightly change the rotation rate and even the tilt over millions to billions of years. The effect is a little like a figure skater pulling in their arms to spin faster, or stretching them out to spin slower, but spread over an entire mantle, and happening over geological timescales, not seconds. On Venus, as mantle plumes rise, as dense material sinks, as the crust is possibly resurfaced in big events, the internal mass distribution is not static. Each shift nudges the rotation very slightly. It's a small effect compared to the atmosphere and the sun's tides, but it's not zero. So where does that leave you when you try to rank the drivers? The big players are still external: solar gravitational tides and massive atmospheric tides. Those are the ones that can flip a spin, slow it dramatically, and hold it near a slow retrograde state. Internal torques from core mantle coupling and changing mass distributions are weaker, more like background noise riding on top of the main tidal signal. But over hundreds of millions of years, even that noise can matter. It can help decide which of the limited stable rotation states Venus finally falls into, and it can influence how the planet moves between those states when conditions change. Right now, though, a lot of this is still educated guesswork, because we do not know Venus's interior as well as we know Earth's. We don't have direct measurements of core size, core state, or detailed mantle structure. We infer most of it from gravity data, density, and analogy with Earth. That's useful, but it's not enough if you want to say with confidence how much of Venus's spin history came from inside versus outside. To really test these ideas, you need seismology on Venus. You need seismometers sitting on the surface, listening to quakes, measuring how seismic waves travel through the planet, mapping out where the core starts, how big it is, whether it's liquid or solid, how thick the mantle is, whether there are big compositional layers or large, dense blobs hanging around deep below the surface. With that, you can build a much more precise model of the moments of inertia, the possible core-mantle coupling, and the internal sources of torque. This is not the science fiction. Proposed future missions from NASA and ESA include concepts for long-lived landers that could carry seismometers, plus improved radar mapping from orbit to tie gravity and topography together. Put that package on Venus, survive long enough in 465 degrees Celsius heat and 90 bar pressure to collect data, and you could finally connect what's happening deep inside the planet to the strange drifting rotation you see at the surface. So the picture that's forming is layered, literally. At the top, a super-rotating atmosphere trading angular momentum with the crust. Outside, the sun's gravity pulling on bulges in rock and air. Inside, a core and mantle with their own slow, persistent interactions, shuffling mass and spin over immense timescales. Venus's rotation is the sum of all of that, not just one mechanism in isolation. And once you admit that, you have to confront one more unsettling idea. If all these layers and forces are interacting, and if some of the end states are only marginally stable, then Venus's spin history might not have been a smooth slide into one final configuration. It might have wandered, chaotically, between different possibilities, with small early differences pushing it into the bizarre state you see now instead of some other equally allowed outcome. What if Venus's rotation isn't some neat inevitable end state, but just the way the dice happened to land this time? You're used to hearing clean stories, tides did this and impacted that, but when you put all the forces together, the system doesn't always behave smoothly. It can behave chaotically, and that means tiny nudges early on can decide whether a planet ends up spinning normally or backwards with a 243-day day. In the early inner solar system, orbits and spins were anything but calm. Planets were still trading energy and angular momentum with each other, and with the leftover debris. When orbital eccentricities, how stretched an orbit is, are higher than today, and when tilts are larger, you get much stronger and more complicated gravitational torques. Models that track this show that a planet's spin axis can wander in a chaotic way under the combined pull of the Sun and the other planets, especially if its tilt and eccentricity cross certain thresholds. For Venus, there's good reason to think its orbit was more eccentric early on, not the nearly circular path you see now. A more stretched orbit means the strength and direction of solar tides change more as the planet moves around the Sun. Combine that with changing obliquity, and the spin axis can get kicked around in a way that's very sensitive to initial conditions. Change an impact angle slightly, or shift the timing of one close approach by a fraction, and over millions of years you can end up with a completely different final spin. When people like Correa and colleagues ran detailed models of Venus's spin evolution, including solar tides, atmospheric tides, and the way these depend on rotation rate and tilt, they found something interesting. You don't get an infinite continuum of possible final spins. For a Venus-like planet with its mass, distance from the Sun, and thick atmosphere, you get a handful of stable attractors, a few slow prograde states, a few slow retrograde states. These are like parking spots in spin space. Once the planet falls into one, it tends to stay there, unless something big moves it out. The punchline is that Venus's current rotation, slow retrograde with a tilt near 177 degrees, is just one of those parking spots. A tiny change early in its history, a slightly different impact, a slightly different orbital eccentricity, a slightly different atmospheric buildup could have nudged it into another attractor, maybe a slow prograde state instead. Same mass, same general orbit, completely different day length and spin direction, just because the early conditions were nudged by what, at the time, would have looked like minor differences. There's another detail that looks spooky but turns out to be misleading if you don't dig into it. Right now, Venus's sidereal day, about 243 Earth days, is numerically close to the 584-day synodic period between Earth and Venus, the time from one close approach of Venus to the next as seen from Earth. If you take 243 and 584, the ratio is close to a simple fraction, and it's tempting to think, aha, resonance, Earth must be controlling Venus's spin somehow. But when you run the dynamics properly, Earth's gravitational torque on Venus's spin is tiny. The distance between the planets during close approaches is tens of millions of kilometers, tens of millions of miles. The Sun's pull dominates by orders of magnitude. The small alignment between Venus's day length and the Earth. Venus' synodic period looks cool, but the numbers just don't support Earth being able to lock or steer Venus's rotation in any serious way. The simplest explanation is that it's a coincidence, one of those numerical near matches that happens in a system with many cycles and many timescales. The deeper message in all of this is that planetary rotation is not as deterministic as the simple disk spins, planet spin done story suggests. Yes, conservation of angular momentum sets broad constraints, but within those constraints, impacts, tides, atmospheric buildup, internal structure, and orbital evolution all interact. When those interactions cross into chaotic regimes, the outcome becomes highly sensitive to small early differences. Venus is the proof sitting next door. It tells you that an Earth-sized planet at an Earth-like scale, in the same basic disk, can end up with a spin that looks nothing like Earth's. That has direct consequences when you start looking beyond the solar system. When you see a rocky exoplanet with roughly Earth's mass and radius, in a roughly similar orbit around its star, it's very tempting to assume an Earth-like day as a default. Maybe something between 10 and 40 hours, prograde, modest tilt. But Venus shows you that this assumption is dangerous. You can have a planet that ticks all the Earth-like boxes on paper, and still ends up with a 243-day retrograde rotation because of a different sequence of impacts, a different atmosphere, a different tidal history. And that spin history matters directly for climate and habitability. A slow retrograde rotation changes how heat is redistributed between day and night, how winds organise, how clouds form, and whether oceans, if they ever existed, can survive or are driven into a runaway greenhouse. Two planets with the same mass and orbit but different spin states can end up with completely different surface conditions, one temperate, one a global oven. So when you look at Venus and call it a cosmic coin toss, you're not just being dramatic, you're recognizing that rotation is the end result of a long, chaotic chain of events. Change that chain slightly and the same basic planet could have presented a completely different face to the Sun. Which leads straight into the next hard question. If rotation and climate can twist each other in this many ways, how much of Venus's hellish atmosphere is a consequence of that spin? And how much of that spin is a consequence of the atmosphere? And could a different rotation history have kept Venus closer to an Earth-like state instead of driving it into a permanent runaway greenhouse? Here's the twist that should bother you now. What if Venus's weird rotation isn't just a physics detail, but one of the main reasons the planet turned into a furnace? And what if that same furnace is still helping to hold the weird rotation in place? At this point, you can't separate how it spins from why it's hell. Start with the basics of a 243-day rotation. That means one side of Venus faces the Sun for months at a time, then spends months in darkness. You don't get a quick day-night cycle like Earth's 24 hours. You get extremely long dayside heating and extremely long nightside cooling. Now drop that into a thick carbon dioxide atmosphere, around 90 bar with global sulfuric acid clouds. Sunlight gets in, the surface and lower atmosphere heat up, but infrared radiation trying to escape gets trapped very efficiently. That's a runaway greenhouse. Because the spin is so slow, the atmosphere has a lot of time to move heat around before the sun sets. Strong global circulation develops. Air rises on the day side, flows toward the night side high in the atmosphere, cools, sinks, and returns near the surface. The result is a nearly uniform cloud deck and a circulation pattern that smears temperature differences out. That's why Venus sits around 465 degrees Celsius, roughly 870 degrees Fahrenheit, almost everywhere day-night, equator, pole. The slow rotation gives the atmosphere enough time to equalize the planet into a global oven. Climate models, full 3D simulations, have pushed on this. When you plug in a Venus-like planet but give it a faster rotation, closer to Earth's, you get a different behaviour. A quicker spin strengthens the Coriolis effect, the apparent force that bends moving air, because the planet is turning underneath. Instead of one dominant super-rotating circulation, you break the atmosphere into more Earth-like jet streams and cells. You get stronger day-night contrast, different cloud patterns, and more localized heat transport. Some of those models suggest that if early Venus had rotated faster, it might have kept oceans, at least for a while. A faster spin could help build a thick dayside cloud shield over the subsolar region, reflecting more sunlight while allowing more efficient cooling on the night side. That combination can delay or even prevent a runaway greenhouse, letting liquid water survive much longer. In that alternate history, Venus might have stayed closer to Earth's climate for a significant fraction of its life, but that's not the path we see. Instead, we have a very slow spin, a planet-wide greenhouse, and a super-rotating atmosphere that laps the solid planet in about 4 Earth days. And here's the key point. The feedback between spin and climate runs both ways. On the one side, the structure of the atmosphere, how thick it is, how it circulates, how clouds form directly affects the tidal torques from sunlight. Thermal tides in a massive CO2 atmosphere shift huge amounts of air around, creating those air bulges the sun can pull on. That helps set the net torque on the planet and pushes the spin towards slow retrograde. Change the climate, change the winds, change the tides, and you change the long-term spin evolution. On the other side, the spin rate sets the length of the day and the strength of the Coriolis effect, which shapes the circulation in the first place. A very slow rotation favours the kind of global super-rotating pattern Venus has now, with clouds and winds wrapped around the whole planet, and that pattern is exactly what you need to drive strong atmospheric tides. So climate and rotation are locked in a loop, the atmosphere helps decide how the planet spins, and the spin helps decide how the atmosphere behaves. To get an intuitive feel for how much energy is involved, think about those winds. At the cloud tops, you're talking about speeds of roughly 360 kilometers per hour, around 225 miles per hour, whipping around a planet about 12,100 kilometers across, roughly 7,500 miles. That's not a local storm, that's the whole atmosphere moving. The angular momentum stored in that moving shell of dense gas is enormous, far beyond any hurricane on Earth. Over billions of years, that atmospheric flywheel, constantly driven by the sun, has had plenty of time to push and pull on the crust and adjust the rotation. Rock feels solid and permanent, air feels light and temporary, but on Venus, the light part is carrying enough momentum to act like a long-term engine on the solid planet. The radar measurements that show minutes of drift in day length over just a few decades are basically you catching that engine in the act, making small adjustments in a system that has already been heavily reworked over geologic time. This is where the whole story shifts. The question, why does Venus rotate differently, is no longer just a question about angular momentum and tidal theory. It merges directly into, why did Venus become uninhabitable, and could it have turned out more like Earth? The slow retrograde spin helps sustain a brutal uniform greenhouse by supporting the super-rotating atmosphere and global cloud deck. The brutal greenhouse, in turn, gives you the dense, hot atmosphere you need to keep driving the spin toward that slow retrograde state and to keep tweaking it. Rotation and climate on Venus are not separate chapters, they are co-conspirators. A different spin history could have delayed or avoided the runaway greenhouse. A different climate history, with less atmosphere, could have left Venus with a more Earth-like spin. Instead, the planet moved into a regime where the two locked together and walked each other steadily toward the world you see now, a planet where a day is longer than a year and the surface is hot enough to melt lead. And just when you think the picture is complete, there is one more missing piece you have to factor in, something Earth has and Venus doesn't: a large moon. If a moon can stabilize a planet's tilt and dominate its tides, what does it mean that Venus has none? And how does that absence fit into the story of its broken rotation? Here's a detail that should bother you. Venus has one of the strangest rotations in the solar system, and it also has no moon at all. That combination is not something you just ignore. When you compare it to Earth, you can see right away that having or not having a big satellite changes how a planet's spin evolves. Look at what Earth's moon actually does. It's big, about a quarter of Earth's diameter, roughly 3,500 kilometers across, about 2,200 miles. Its gravity raises tides in our oceans and in the solid Earth. Those tides are not perfectly aligned with the line between Earth and the Moon. Earth's rotation drags them a bit ahead. The Moon pulls on those offset bulges, and that pull breaks Earth's rotation and slowly transfers angular momentum to the Moon's orbit. Over billions of years, that has lengthened Earth's day from maybe 5 to 6 hours early on to the 24 hours you know now, and has pushed the Moon out to about 384,000 kilometers, around 239,000 miles away. The Moon also stabilizes Earth's tilt. Interactions between Earth, the Moon and the Sun keep Earth's obliquity oscillating in a fairly narrow range around 23 degrees. Without a big moon, simulations show Earth's tilt could wander much more, even swinging tens of degrees over millions of years. That would mean much more chaotic climate changes and a more unstable spin axis. So on Earth, the moon is not just a pretty object in the sky, it is a stabilizing anchor for both rotation rate and tilt. Now compare that to Venus. Venus has no confirmed natural satellites. In the 1700s and 1800s, there were claims of a Venusian moon, sometimes called Neith, but with better telescopes and more careful tracking, those supposed moons turned out to be background stars or observational mistakes. Modern observations from ground and from spacecraft show no moon, no ring, nothing. Venus is alone. That simple fact narrows your options. Either Venus never had a giant impact that left a long-lived moon, or it did have a big impact, but the debris never formed a permanent satellite. Given how important giant impacts seem to be elsewhere, that second option is serious, which is why people run specific simulations for Venus plus impact. In those models, when a Mars-size or smaller body hits Venus at the right angle and speed, you can flip or strongly slow the planet's rotation, but the debris behaves differently from Earth's moon-forming case. If most of the ejected material ends up inside the distance where an orbit would match Venus's rotation period, the synchronous orbit, then the debris doesn't stay up. Gravitational interactions and drag effects pull it back down and it falls back onto the planet instead of forming a stable satellite like the moon. You get a twisted spin but no moon. Some simulations even show that the more you flip or slow the spin, the easier it is for the debris to recrete, because the synchronous distance moves in the region where stable orbits can form changes. That lines up well with what you see at Venus: extreme rotation, no moon. It doesn't prove a specific impact happened, but it shows that impact plus no satellite is a physically realistic outcome. Now think about how that lack of a moon changes the long-term forces on Venus's spin. Earth has three main tidal players: the Moon, the Sun, and the atmosphere, and the Moon is the strongest. Venus only has the Sun and the atmosphere in that list. There is no lunar tide trying to slow the planet in a simple prograde way, and no lunar torque helping to keep the tilt in a narrow range. Without a big moon, Venus's spin evolution is dominated by solar gravitational tides and atmospheric tides. The Sun's gravitational tide is always trying to break the rotation and drive it toward a tidally locked or resonant state. The atmospheric tide, driven by sunlight heating that 90 bar CO2 atmosphere, is always trying to move mass around in a way that can favour slow retrograde rotation. There is no strong external satellite tide to lock in a more Earth-like prograde spin, or to hold the axis in a stable, moderate obliquity. So where Earth gets a clear prograde tidal break that gradually lengthens the day but keeps the spin direction and tilt sane, Venus gets a more complicated tug-of-war between the Sun and its own atmosphere. That frees it up dynamically to fall into one of those slow retrograde end states, instead of marching along a path similar to Earth's. The missing moon doesn't cause the backward spin by itself, but it removes a major stabilizing and controlling influence, and that changes what the dominant torques can do over billions of years. From a forensic point of view, the absence of a moon around Venus is a real clue. If Venus's rotation is the result of a giant impact, that impact must have played out differently from the Earth-Moon event, with most debris falling back in instead of forming a long-lived satellite. That difference could be due to impact angle, impactor size or timing, but it could also be tied to Venus's distance from the Sun and its atmosphere. Closer to the Sun, solar tides and radiation forces are stronger, which can destabilize small orbits. A thick atmosphere can also interact with any low-altitude debris and help pull it down. If, on the other hand, Venus's spin came mostly from tides and atmospheric evolution without a dominant impact, the lack of a moon is still important, because it means nothing stepped in to stabilize the tilt or to steer the spin toward a more familiar state. Either way, the missing satellite is not just a footnote, it's part of the explanation for why Venus, out of all the inner planets, is the one that ended up in a slow retrograde configuration. So when you look up and see Venus as a bright point with no companion, that emptiness is telling you something. It's telling you that whatever happened to Venus, whether it was slammed early and then reshaped by tides, or twisted primarily by long-term interactions with the Sun and atmosphere, it went through that history without the stabilizing hand of a big moon. And that made it easier for the planet to slide into the strange rotational state you see now. Which brings you to the next step. If you want to go beyond clues and really test all these origin stories, you can't just stare from far away anymore. You have to replay Venus's life in detail inside computers, with all the known forces included, and see which combinations of impacts, tides and atmospheres can actually reproduce the rotation we measure today. At this point, you've heard a lot of separate pieces: impacts, tides, atmosphere, interior. The honest way to ask, why does Venus rotate like this, is to throw all of those into one big test and see what survives. That's what simulations do. They roll the clock back inside a computer, give Venus different starting spins, different impacts, different atmospheres, and then let the physics run forward for billions of years to see which stories actually land you on the world we see today. Here's how that works in practice. Researchers start with the basics: Venus's mass, about 81.5% of Earth's, its radius, about 6,052 kilometers, roughly 3,760 miles, and its orbit, 0.72 AU from the Sun, around 108 million kilometers, about 67 million miles. They set up spin evolution codes that include the key torques, gravitational tides from the Sun, atmospheric tides from thermal heating, possible torques from core mantle coupling, plus the option to inject big kicks from giant impacts at specific times. They then pick an initial spin state, maybe a fast prograde rotation like young Earth, a slower spin, or even an early retrograde state, and let the simulation run forward for the billions of years of model time. As the virtual Venus orbits the Sun, the tides reshuffle angular momentum, the atmosphere grows or changes, and the rotation rate and tilt evolve step by step. At the end, they check what kind of day length and obliquity they get, and whether it looks anything like Venus's current approximately 243-day retrograde rotation and approximately 177-degree tilt. The surprising part is that there isn't just one special starting condition that works. You might expect that only a very specific initial spin or a very specific impact, would lead to the exact weirdness we see. Instead, what the models show is that a lot of different beginnings can converge on a Venus-like ending, as long as you have strong solar and atmospheric tides acting for a long time. Start the planet with a fast prograde spin, and solar tides plus a thick atmosphere can gradually slow it, flip it, and park it in a slow retrograde state. Start it with a more moderate prograde spin, same story. Even start with an early retrograde spin, maybe from a giant impact, and the same tidal processes can still nudge it toward a similar slow retrograde equilibrium. The details of the path differ, but the final spin state looks very similar. That's a big deal, because it means the rotation we see today is not a sharp fingerprint that points to one unique origin event. Then people went a step further and added climate to the mix. They coupled the spin evolution codes to 3D climate models that track how water behaves, how clouds form, when a runaway greenhouse kicks in, how fast oceans, if they ever existed, would be lost. In those runs, you don't just evolve spin, you evolve atmosphere and temperature at the same time. What you see there is even more degeneracy. Different spin histories can still end up with very similar present-day hellscapes, thick CO2 atmospheres, global sulfuric acid clouds, surface temperatures around 465 degrees Celsius, about 870 degrees Fahrenheit. One path might keep surface water for a few hundred million years, another might lose it earlier, but both can still lead to the same modern Venus: slow retrograde spin, no oceans, runaway greenhouse. Some trajectories pass through short windows of temperate conditions, others slam into the greenhouse faster. That's where the cutting edge is now, trying to link how long could Venus have been habitable to specific rotation histories, not just final states. All of this only matters if the models are constrained by real data. So any scenario that claims to explain Venus has to hit a tight list of targets. It has to reproduce the observed day length, about 243.02 Earth days, not just some slow value. It has to give you retrograde rotation, not just slow prograde. It has to allow for small variations in day length, those minutes of drift over decades that we see in radar and spacecraft data. And it needs to leave Venus in a near circular orbit, like the one we measure today, not a highly eccentric one. That's a tough multi-dimensional fit. When you filter through all the runs, the only ones that come close to matching all of those constraints are the scenarios where Venus has a dense atmosphere and strong thermal tides, and often where it also experiences one or more early giant impacts that give it a big spin kick. You can get slow retrograde without an impact, but it's easier and more robust in the models, if you let an early collision push the planet into the right regime, and then let tides do the rest. So what do these simulations actually tell you in plain language? They say Venus's weird rotation is not a crazy fluke that needed a 1 in a billion accident. Given enough time, a big enough atmosphere, and strong enough gravitational leverage from the Sun, a planet like Venus is naturally driven toward one of a small set of slow spin states, and a slow retrograde state very much like the one we see as one of the most natural endpoints. That doesn't make Venus boring, it makes it more dangerous conceptually. It means that if you take an Earth-sized planet, move it inward a bit, let it build up a thick greenhouse atmosphere, and let tides and climate interact for a few billion years, you shouldn't be surprised if you end up with something that looks a lot like present-day Venus. Slow retrograde spin included. What felt like a one-off freak case starts to look like a predictable outcome of the same physics you see everywhere. And once you realise that, you can't keep the story confined to our solar system. If a Venus outcome is dynamically natural for a world like this, then you have to ask how many of the rocky planets we've already detected around other stars are on that same path, and how many of the Earth-like worlds we dream about are actually much closer, in spirit, to a slow-spinning, cloud-wrapped Venus than to our own planet. Here's where Venus stops being just a weird neighbour and turns into a warning label for a whole category of planets we're already finding around other stars. If this can happen here, there is no reason it can't happen elsewhere, and in a much more extreme way. Look at what our exoplanet surveys are actually finding. A huge fraction of the planets we know are close-in, high-temperature worlds, hot super-Earths and mini-Neptunes, orbiting their stars at distances smaller than Mercury's orbit. Some of them go around their star in just a few days. That puts them at distances like 0.05 astronomical units, about 7.5 million kilometers, roughly 4.7 million miles from their star. At those distances, tidal forces are far stronger than anything Venus ever experienced at 0.72 astronomical units. So here's the key thought experiment. If Venus can be slowed down to a 243-day retrograde rotation at 0.72 astronomical units, with the Sun's tides and a 90-bar atmosphere, what can the same physics do to a rocky planet twice Earth's mass, buried at 0.05 astronomical units in its star's gravity well? The answer is, it can do almost anything within the limits of physics, from complete tidal locking to very slow forward spins to slow retrograde spins, depending on the atmosphere and early impact history. Venus proves slow retrograde is not exotic, just one outcome in the menu. Right now, when people talk about these close-in exoplanets, the default assumption is simple: tidal locking. One side always faces the star, permanent day on one hemisphere, permanent night on the other. Climate models are built on that picture, with a blazing hot day side and a cold night side, maybe with a narrow terminator band in between where temperatures are moderate. That's useful, but Venus shows you there is another option you cannot ignore. Venus is not tidally locked. It rotates slowly, retrograde with a day longer than its year, and its atmosphere is the reason it sits in that particular state instead of deadlocking to the Sun. That means that for close-in exoplanets, especially those with thick atmospheres, you have to consider Venus-like rotation states, very slow, possibly retrograde, but not perfectly synchronized with the orbit. The climate on such a planet is nothing like the simple day-night split of a locked world. On a tidally locked planet, you get a permanent substellar point where the star is always overhead, and you build your whole climate picture around that fixed hot spot. On a Venus-like slow spinner, the substellar point moves very slowly across the surface. The atmosphere has time to circulate to move heat to form global cloud decks. You can end up with cloud shields that sit over the slowly migrating day side, reflecting a lot of incoming light, and circulation patterns that move heat around far more evenly than in a locked case. That changes where and whether habitable zones might exist, maybe along the terminator, maybe under persistent reflective clouds. This is where rotation becomes a hidden climate variable. When you see an exoplanet in the data, you usually get mass, radius, and maybe a rough idea of its orbital distance and stellar type. From that, you immediately jump to the question, could it have liquid water? You look at the amount of starlight it gets and compare it to Earth. So without knowing its rotation rate and obliquity, you're missing a huge piece of the picture. Venus is the perfect example. On paper, it's not that far from the inner edge of our traditional habitable zone. It's close to Earth in size and mass. If you saw it from far away and only knew those numbers, you might put it on a list of Earth-like candidates. But the actual planet has a 243-day retrograde spin, a small effective tilt, a global super-rotating atmosphere, and a runaway greenhouse. All of those are tied to rotation. Change the rotation, and you could change the entire climate history. Keep the orbit and size the same, and you can still get anything from a temperate ocean world with a faster spin to the global pressure cooker we see now with a slow, retrograde one. The challenge is, rotation is hard to measure directly for exoplanets, especially small rocky ones. You can't just watch the surface features move the way we do for Mars or Jupiter. Instead, you have to look for indirect signatures. One of the main tools is thermal phase curves, how the infrared brightness of the planet changes as it orbits the star. A tidally locked planet with a fixed hot day side and a cold night side produces one kind of phase curve. A slowly rotating planet with a thick atmosphere that shifts heat around produces another. If you understand how Venus's slow retrograde spin imprints itself on its climate, temperature distribution and cloud cover, you can build better models of what those different phase curves should look like. That means when telescopes like the James Webb Space Telescope and future missions after it give you temperature maps and phase variations for hot super-Earths, you can start asking, is this planet locked, or is it more like a slow-spinning Venus analogue? There are other observables too, like how quickly the planet's day side heats up and cools down as it goes in and out of view, whether there are strong east-west offsets in the hotspot position, and whether the observed spectra show signs of thick reflective clouds. All of these are easier to interpret if you've already done your homework on the one slow, backward, atmosphere-driven planet you can actually study up close, Venus. So here's the punchline you shouldn't ignore. Every time we talk about Earth-like exoplanets, we are quietly assuming something big, that they are not like Venus in rotation. We assume their days are not hundreds of hours or hundreds of days long, that they are not retrograde, that their atmospheres are not driving them towards strange, slow states. Venus is your warning that this assumption is not safe. One twist in spin history, one different impact, one thicker atmosphere, and you can turn an Earth-sized planet at a seemingly reasonable orbit into a slow-spinning permanent greenhouse. That means that when we say this world is in the habitable zone, we really mean this world gets about the right amount of light. Whether it actually uses that light to stay temperate or to cook itself solid depends on details like rotation and atmosphere that you can't see in a quick catalogue. Venus is the nearby proof that those hidden details can flip a planet's story from maybe habitable to definitely hellish. And that brings you all the way back home to the question that started this whole chain. If impacts, tides, atmosphere, interior, and even chaos all work together to make Venus what it is, what is the simplest way to sum up why this one planet, almost a twin of Earth, ended up rotating backward upside down and so slowly that its day is longer than its year? So after all of this, what is the actual answer? Why does Venus rotate differently? Strip it down and it comes to this. Venus's spin has been hammered and reshaped for billions of years by three main things working together: early chaos and likely giant impacts, relentless solar tides, and a huge dense atmosphere that refuses to just sit there and behave. Those three together took a planet that probably started with a normal fast prograde spin like Earth, and dragged it into a slow retrograde, almost upside down state, then kept it hovering there. Start with the early chaos. The young inner solar system was full of big bodies, some Mars-sized, crossing orbits and hitting each other. Venus, almost Earth-sized, was a prime target. In that environment, it is very likely Venus took at least one massive impact, maybe more, with an impactor a few percent to a few tens of percent of its own mass, slamming in at 10 to 30 kilometers per second, roughly 22,000 to 67,000 miles per hour. A hit like that doesn't just dig a crater, it dumps a huge amount of angular momentum into the planet. Depending on the angle, it can slow the spin, tilt the axis, or even flip the rotation from prograde to retrograde. Some of those impact simulations do something very specific that matches Venus. They change the spin dramatically and don't leave a big moon behind. If most of the debris stays inside the synchronous orbit, it falls back in instead of forming a satellite. That matches what you see, a planet with a strange rotation and no moon. So the simplest picture is, early on Venus was knocked off its original spin path, maybe flipped, maybe just slowed and tilted far away from the default state that a quiet disk would have produced. Then you let time do its work. After the big impacts, Venus is sitting there, close to the Sun at 0.72 astronomical units, with a thickening atmosphere and a non-standard spin. Solar gravitational tides go to work on the solid body. They always do the same basic thing. They try to slow the rotation and push the planet toward a state where the same side always faces the Sun, or toward a simple resonance close to that. On a bare rock like Mercury, that can lead to a stable spin orbit resonance, 3 rotations for every 2 orbits, all prograde. But Venus isn't a bare rock. Its atmosphere grows into a roughly 90 bar, CO2-dominated monster. Sunlight heats that atmosphere day after day, and because the planet rotates, that heating moves around. The result is strong thermal tides in the air, pressure waves that shift huge amounts of mass. Those moving air bulges feel the sun's gravity too, and the sun pulls on them, adding another torque to the system. In Venus's case, that atmospheric torque tends to favour slow retrograde rotation. When you put the math together, you don't get an infinite menu of final spins. For a Venus-like planet, you get a small set of stable end states. A few slow prograde options, a few slow retrograde options. The combination of early spin, any impacts, solar tides and atmospheric tides steers the planet into one of those states over billions of years. Venus ended up in a slow retrograde one, with a sidereal day of about 243.02 Earth days, an axial tilt of about 177 degrees, and a solar day sunrise to sunrise of about 116.75 Earth days. That's the equilibrium it fell into, given its mass, its orbit, and its atmosphere. Crucially, that equilibrium is not perfectly frozen. Even today, the rotation is still being adjusted. The atmosphere super-rotates, with cloud tops circling the planet in about 4 Earth days at around 360 kilometers per hour, roughly 225 miles per hour. Those winds slam into highland regions and generate mountain waves, large stationary disturbances in the atmosphere tied to surface features. Those waves, plus friction between the air and the ground, let the atmosphere trade angular momentum with the solid planet. When global winds speed up, the atmosphere takes on more angular momentum, and the solid surface has to slow very slightly to keep the total budget balanced. When winds slow down, the planet can speed up a little. That exchange shows up as the few-minute changes in day length we see when we compare Magellan's measurements from the 1990s with Venus Express and ground-based radar from the 2000s and 2010s, differences of about 6 to 7 minutes over 16 to 29 years. On top of that, you have smaller internal effects, core mantle coupling and slow shifts in mass inside the planet, tweaking the moments of inertia and adding tiny corrections. So the rotation we measure, 243.02 days retrograde with fluctuations, is not some untouched fossil from a single event. It is a snapshot of a process that started in early chaos, was shaped by billions of years of tides under a crushing atmosphere, and is still being fine-tuned now by winds and internal dynamics. Venus's spin is a living parameter, not a dead relic, and that's the real hook. When you say Venus rotates differently, you're not just pointing out that its day is weird, you're summarizing an entire alternate history for an Earth-sized world. You're saying here is a planet that was probably born spinning in the normal direction, got knocked off that path by violent impacts, then was slowly resculpted by solar tides and a massive runaway greenhouse atmosphere into a slow retrograde state that looks impossible at first glance, but actually falls right out of the physics if you let it run long enough. If you could rewind the solar system and run it again, change the timing of one impact, change how fast Venus's atmosphere thickened, tweak its early orbit a little, you might end up with a very different Venus. Maybe a world with a faster prograde spin, a stronger Coriolis effect, more Earth-like jet streams, maybe even long-lived oceans and a moderate climate. Instead, in this version, we got a planet where a day is longer than a year, the sun rises in the west, and the atmosphere is so massive and so fast that it has literally grabbed the solid planet and turned its rotation backwards. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect like the video, and subscribe to the channel for more such amazing videos.